Hello friends, welcome back to the channel. Today we are going to discuss one of the most important storage concepts in Kubernetes, that is persistent volumes. But before we jump into persistent volumes, let's do a quick recap of what we have already learned about volumes in Kubernetes. Well, we already know, just like Docker containers, pods in Kubernetes are temporary, means transient in nature. That means if a pod gets deleted, restarted or recreated, everything stored inside that pod is gone. And this creates two major problems. Problem 1, data loss. If your application stores data inside the container and the pod restarts, boom, the data disappears. So anytime the pod is deleted or restarted, the data is lost. This is a big issue for applications like databases, logs, uploads and user files. The second problem is data sharing across replicas. Now imagine you have multiple replicas of same application running. For example, you scale your deployment from 1 to 3 pods. Now the question is, how will all these pods share the same data? Because by default, each pod stores data inside its own container, and that data is not accessible to other pods. So without volumes, pods cannot share data, and each replica has its own isolated storage. So this is where Kubernetes volumes come in. With volumes, we solve both major issues. First, data stays safe even if pod restarts, and second, multiple pods can access and share the same data. So a volume is basically a directory with data which is accessible to the containers inside a pod. So instead of storing data inside the container, we store it inside a volume. Now the question is, how do containers use a volume? Once a volume is created, we mount it inside the container, meaning the volume is attached to the pod and the container accesses it through a folder path. So whatever data the container writes to the mounted directory gets stored inside the volume. Even if container gets deleted, restarted or recreated, the data inside the volume remains safe. Well, in our previous videos, we also saw how to store data at the pod level instead of storing it inside the container using the mtdir volume. In the last few videos, we understood mtdir, config maps and secrets, and these are all ephemeral types of volumes, meaning if the pod gets deleted or the node goes down, the data associated with these volumes also gets deleted. Now with mtdir, we still face the same challenges, sharing data across multiple pods and persisting data when the pod restarts. And because of that, we again run into the same data loss problem. That's where persistent volumes come into the picture. Persistent volumes allow us to store data in external storage, means outside the pod or node. For example, AWS EBS, SAN storage, NAS storage, etc. The key point is persistent volumes do not depend on any individual pod or node using them. So in Kubernetes, a persistent volume or PV is basically a pool of storage available inside the cluster. And these storage can be created in two ways, manually by the cluster administrator or dynamically by Kubernetes using storage class. Now here is something important. Developers or DevOps engineers don't directly use the PV. Instead, they create something called a PVC, persistent volume claim. A PVC is simply a request for storage, like saying, hey Kubernetes, I need 5 GB of storage and I want it to be read-write once. Once the PVC is created, Kubernetes automatically finds a matching PV and binds them together. And finally, when we deploy our application, the pod doesn't mount the PV directly, the pod mounts the PVC, and through that PVC it gets access to the PV storage. So in a high availability setup where you want scalability and fault tolerance, storage becomes a big challenge. Because when your application scales, your pods can run on different nodes. And in that case, you need a shared storage that is independent of the worker nodes. So no matter where the pod runs, it should still be able to access the same data. To achieve this, in Kubernetes, we need a few additional storage objects. Well, Kubernetes offers 3 key components to persist data, even if pods restart or nodes fail. First one is persistent volume, second persistent volume claim and storage class. Now let's understand these one by one. First thing we need is a persistent volume. A persistent volume basically tells Kubernetes how much storage is available and how Kubernetes should connect to the backend storage. Also, PV types. Kubernetes supports many different PV backends. For example, AWS Elastic Block Store, Azure Disk, NFS, local storage, and many more. You can find the complete list in the official Kubernetes documentation. Now let's create a simple persistent volume using NFS. Let's head back to the IDE where my Kubernetes repo is already available. All the PV related manifests for this demo will be under day 14 directory. Now I will create a YAML file named seh-pv.yaml. Just like any Kubernetes resource, a PV manifest has 4 mandatory fields. First one is API version, then kind, metadata, and spec. We can confirm the API version and the kind for persistent volume using kubectl API-resources pipe grep pv command. So as you can see here, kind is persistent volume, short name is PV, and API version is v1. Let's update the manifest file. Kind is persistent volume, version is v1. Under metadata, I will give the PV a name seh-pv. Now inside the spec, we define the actual PV configuration. First, we define how much storage this PV provides using capacity storage 500 MI. So in Kubernetes, storage can be defined in MI, megabytes, GI, GB bytes, even TI, terabytes. For this example, I will use 500 MI, that is 500 megabytes. Next, we define how pods can access this PV using access modes. For now, I am giving read write many. Well, this is very important concept because access modes decide whether one pod can use it, multiple pods can share it, also pods across nodes can access it. For this demo, I will use read write many, meaning multiple pods on multiple nodes can mount it in read write mode. The available access modes are read write once, read only many, read write many, read write once pod. Let me quickly explain these. Read write many. Best for shared storage like NFS, multiple pods across multiple nodes can read write. Then read write once. The volume can be mounted read write by only one node. So if your pods run on different nodes, they won't be able to share it. Read only many. Many nodes can mount it, but only in read only mode. Read write once pod. Only a single pod in the entire cluster can mount it read write. One important note: not every storage backend supports every access mode. For example, NFS supports read write many, which is why it's commonly used for shared storage. Next, we define storage class name. This is simply the name Kubernetes uses to group persistent volumes and connect them with persistent volume claims later. Finally, we define the backend storage type. In this example, I am using NFS. This NFS section tells Kubernetes this persistent volume should be accessed using the NFS protocol. Quick reminder, in my previous video, I already showed how to set up an NFS server. That NFS server is running outside Kubernetes and I created a shared directory /data/seh-pv. Now I am simply using the NFS server IP address, that is 192.168.0.7, and I am telling Kubernetes to use that exported path as persistent storage. Since I am maintaining everything in Git, I will push these changes using git add dot git commit -m pv created and git push. Well, this is our complete persistent volume manifest file. One important point to note here is persistent volumes are not namespaced. That means a persistent volume is created at the cluster level and it can be used by workloads from any namespace in the cluster. Now on the Kubernetes master node, I have already cloned my Kubernetes playlist repository and I am inside the repo directory. So first I will just run a quick git pull. Next, let's verify the files. Now you can see day 14 directory is available. Now let's create the persistent volume using kubectl apply -f day 14 seh-pv.yaml. Hit enter. You will see persistent volume is created successfully. To verify, run kubectl get pv. So here you will see details like capacity, access modes, reclaim policy and the current status. Right now the PV status will show as available. That means this persistent volume is created successfully, but it is not bound yet to any persistent volume claim. You can also see access mode is read write many. Capacity is 500 MB. And once again remember, persistent volumes are cluster wide resources. They are not tied to any specific namespace, so they can be used across the entire cluster. So now that our persistent volume is ready, the next step is to create a persistent volume claim. Because remember, a pod cannot directly use a persistent volume. Instead, it requests storage using a persistent volume claim, and Kubernetes connects that persistent volume claim to a matching persistent volume. A persistent volume claim is actually very simple to define. So in IDE, under day 14 folder, let's create a new file, seh-pvc.yaml. Just like any Kubernetes resource, we have 4 mandatory fields. First one is API version, then kind, then metadata, then spec. For PVC, API version is v1 and kind is persistent volume claim. Under metadata, I will give the PVC a name. So let's give it seh-pvc. Now inside the spec, we define access mode, storage class name and requested storage. The storage class name is very important because it helps Kubernetes find the correct persistent volume. For example, we can request 100 MI like this. When we apply this PVC, Kubernetes will now search for the persistent volume that matches the claim. It checks things like storage class name, access mode and capacity. So in our case, Kubernetes will look for a persistent volume with storage class name seh-pv and access mode read write many and at least 100 MB capacity. Once it finds a match, Kubernetes binds that persistent volume claim to the persistent volume, and now both are connected. There is a very common confusion when people start working with Kubernetes storage. Let's say in our persistent volume claim, we request storage as 100 MI. Now the question is, how will Kubernetes bind a persistent volume for this request? Here is the key point. Even though we requested 100 MI, Kubernetes does not create or allocate exactly 100 MI. Instead, Kubernetes will bind the PVC to a full persistent volume that already exists. For example, we already have a PV of 500 MI. Then Kubernetes will bind our PVC to that full 500 MI PV. So the persistent volume claim does not take only 100 MI. What does storage 100 MI actually mean? It simply means I need at least 100 MI of storage. So how Kubernetes selects the persistent volume? Kubernetes will always try to bind the persistent volume claim to the smallest persistent volume that satisfies the request. So for example, we have two persistent volumes. One is of 300 MI and another is of 500 MI. If both match access modes, storage class name and other requirements, then Kubernetes will bind the persistent volume claim requesting 100 MI to the 300 MI persistent volume because it's the smallest one that meets the request. Now I will save the file and push it to Git using git add dot git commit -m and git push. Once done, now back on Kubernetes master node and I will pull the latest changes using git pull command. And apply the persistent volume claim manifest using kubectl apply -f day 14 folder, then manifest file name. Hit enter. You will see the persistent volume claim is created successfully. Now if we check the persistent volume, let's clear the screen and kubectl get PV, you will notice something important. The PV status is no longer available. It will now show as bound and it will show that it is claimed by PVC, that is seh-pvc. Now let's verify the claim itself using kubectl get PVC and you should see seh-pvc is created and bound. Now one important thing to understand in Kubernetes is that persistent volume claims are namespace specific. So if you create a PVC inside one namespace, it will not be visible in another namespace. First, let's check which namespace our current kubectl context is using. We can do this by using kubectl config view command. This command shows the namespace currently set in our kubectl context. For example, seh-students-deploy.yaml. So right now we are working inside the seh-students-deploy.yaml namespace. Now let's switch to default namespace and check if the PVC is visible there. To switch namespace, we use kubectl config set context --current --namespace is equal to default. Now hit enter. Now we have switched to the default namespace. So if we again run kubectl config view, so it shows default namespace. Now if we run kubectl get PVC command, you won't be able to see any PVC because again PVC is tied to the namespace where it was created. Now let's switch back to our namespace, for example seh-students-deploy.yaml using kubectl config set context. Now when we run kubectl get PVC, we can see our PVC is back. One more important thing to notice here, even though in our PVC manifest we requested only 100 MI, the PVC capacity is showing as 500 MI when we do kubectl get PVC, and that's because our persistent volume has a total capacity of 500 MI here. So here is the key concept. A persistent volume claim does not take only a small portion of a persistent volume. Instead, when a PVC binds to a persistent volume, it claims the entire persistent volume. The value we specify in the persistent volume claim, like 100 MI, is basically a minimum requirement. So Kubernetes simply checks if there is a persistent volume available that has at least 100 bytes and matches the access mode and storage class name. If yes, it binds the persistent volume claim to that persistent volume, and once it binds, the claim gets the full persistent volume capacity. Now our persistent volume and persistent volume claim are ready. Let's use them inside our seh-students deployment to store application logs. I have already prepared the deployment file seh-students-deploy.yaml under day 14 directory. Let's go through it step by step. We are creating two replicas of our application. The deployment is in seh-students-deploy namespace. Pods are labeled as type seh-backend. Inside the pod spec, we define volumes and volume mounts. Here under volumes, claim name points to the PVC we created earlier, that is seh-pvc. We are not mounting NFS directly. Kubernetes will handle that automatically through the PVC. the persistent volume bound to this persistent volume claim will be attached to the pods. And then we mount it inside the containers. Here mount path is the folder inside the container where the persistent volume will appear. Any data written here will be stored persistently in the persistent volume. We are using an init container which runs before the main application container. Its job is simply to create the logs directory inside the mounted persistent volume. This ensures that when the application starts, the folder exists and is ready for logging. Don't worry about init containers for now. I will explain them in detail in a separate video. Here inside the main container, you will notice environment variable logging file name. Since we are having two replicas, means two pods will run simultaneously. Each pod writes logs to its own file inside the persistent volume. This ensures logs from one pod don't overwrite logs from another. All logs are stored persistently in the NFS-backed persistent volume. To summarize, volumes and the volume mounts connect pods to persistent storage. Persistent volume claim binds the deployment to persistent volume. Init container sets up the logs folder before the application starts. Each pod writes logs to its own file safely stored in the persistent volume. This is a real-world pattern for applications that generate logs or any data that needs to be survive pod restarts. Finally, save your changes and push the manifest file to GitHub using git commands. Now back on the Kubernetes control plane, let's pull the latest changes and apply our deployment. Git pull and kubectl apply -f day 14 seh-students-deploy.yaml. Since the deployment already exists, you will see something like deployment.apps seh-students-deployment configured. Verify the deployment using kubectl get deploy command and check the pods using kubectl get pods. Once the pods are ready, we can exec into one of the pods using kubectl exec -it, then pod name --bin/bash. So go to the location where the persistent volume is mounted. cd/data/sh-pv. Do ls. You will see logs directory. Inside cd logs, inside there are .log file for each pod. Don't worry about how these files are created. The application in Java controller handles that. Here we are focusing on the persistent volume use case, storing logs persistently. Since this persistent volume is NFS-backed, the files are stored on the NFS server. So on the NFS server, that is 192.168.0.7, cd2/data/seh-pv and do ls. You will see the same logs file proving that the storage is shared across the cluster and persistent even if pod restarts or move to another node. So in this session, we used persistent volume and persistent volume claim to provide shared persistent storage, mounted it in the pods using volume mounts. Logs from each pod are stored persistently in the NFS server. This is a real world use case of persistent volumes in Kubernetes. Well, that's all for today's session. If you have any questions, drop them in the comments. If you found this video helpful, don't forget to like, share and subscribe to the channel. See you in the next video, and in the meantime, happy learning!